This this topic is alternate logic gate representation. Alternate logic gate representation sounds like quite a handful of the topic, but it's actually quite simple. Alternate, it means that we have a different way of recognizing each gate. This is a very straightforward topic, so don't be concerned. Here are our gates. So we know we have the AND gate, the OR gate, an AND, a NOR, which are not basic gates, they're combinations of AND, OR, and inverted. So these are the five gates that we're concerned with. So these are some basic gates or combinations of basic gates. And if we took some time and we gave some thought to this, we could do a truth table for this AND gate. We can do a truth table for this alternate of an and we would see that it is exactly the same. So these are the same thing. And this is the same as this. 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 That's what alternate logic gate representation means. So whatever's on the left-hand side is the same as what's on the right-hand side. So right now, you're just trusting me that that's true. If you want to pause this video, do the truth tables, you will see that it is indeed true. For example, this NAND, this is an AND gate with an inverter, which makes it a NAND gate. So you can see that what comes out of it is ANDed with a invert over the top. So it's a NAND. And what comes out here, so this is A inverted and B or B inverted. So A inverted or B inverted. Then we use De Morgan's theorem. And it's sort of a reverse of De Morgan's theorem. And we can see that that is the same as AB all inverted. This one here, this is an OR gate, but the alternate for the OR gate is an AND gate where everything's inverted coming in and inverted coming out. And from this, we can do De Morgan's. So what is coming out is A inverted and B inverted. All inverted again is the same as A inverted or B inverted, break up the top inversion line. Remember, this is De Morgan's theorem from before the midterm. And then we also have a theorem that says if there's a double inversion of the same length, then it cancels itself out essentially. So we get A or B, and that's what we wanted because this is an OR gate. So it is the same thing. So these down this side is the alternate representation of the gates down this side. And it's pretty handy. Now, how do you do this? Let's say you are approaching a final exam and I say, draw the alternate logic gate representation of an AND gate. So an AND gate looks like this. Here's our AND gate. And to make the alternate, here's what you do. Here's the secret. You have to change the shape of this gate in the middle, make it an OR shape instead. And then if the inputs were not inverted, you're going to have to invert them. And if the outputs were not inverted, you're going to have to invert them. So that's what you get over here on this side is that you have changed the shape in the middle and these were not inverted before, and now I'm going to invert them. Let's say on your final exam, you've got an OR gate, and I'm asking for the alternate logic representation of an OR gate. Well, first change the shape. So it used to be an OR shape, change it to an AND shape. And these are not inverted inputs and outputs, and I want to, yes, invert the inputs and outputs. So you do two steps. First, you change the shape, and then you turn any non-inverted to inverted and vice versa. And that's all there is to it. So let's do this one. You have an AND gate on your final exam. Give me the alternate logic representation of the NAND gate? Well, it used to be an AND shape, change it to an OR shape. It used to be uninverted on the inputs, change it to inverted. Inverted means this little circle. It used to be inverted on the output, so change it to not inverted on the output. That's the alternate. Figure out the truth table. You will find that it is true. Please find the alternate logic representation of an OR gate. Well, change the shape to an AND because it used to be an OR shape. The inputs were not inverted, so now make them inverted. The output was inverted, so now make it, the output was inverted. The output was inverted, so now make it not inverted. And the inverse is a little bit tricky because you don't change its shape. So it was already a triangle shape, keep it as a triangle shape, but the input was not inverted, so I'm going to invert it. The output is inverted, so the output is inverted, so I'm going to not invert it. And that's how you find the alternate logic gate representation of these gates.